All right, today we're going to talk about Newton's laws of motion. There are 3 laws that you will need to know, and I'm asking that you know each of them by both name and number. So the first law is called the law of acceleration. This law states that if we have an object that is at rest, that object will stay at rest unless acted upon by an unbalanced force. If we have an object that is in motion, then that object will continue its motion unless acted upon by an unbalanced force. This is what Newton's first law says. Now, when we interpret this law, I want you to think back to the free body diagrams that we've already learned how to draw. If I have an object who has balanced forces, then this object will not experience an acceleration. If I attempt to move the object by applying a force, but it is experiencing friction of equal magnitude, then this object will not go into motion, assuming that the object is at rest. But if I have an object that's already moving, so let's say I have a ball that is rolling, okay? If that ball is already in motion, then that object experiencing a net force of 0, or if I am applying a force to this moving object, but the object is also experiencing a frictional force, and these are of equal magnitude, then my object will not change its motion. In other words, there is no acceleration unless there is an unbalanced force acting on our object. And then we're very specific here in the little reading. It says the object in motion will stay in motion at the same speed and in the same direction. So remember, constant motion means constant velocity. If we have an acceleration, then the speed or the direction will change. So when we say that there is no change in motion, we're saying that there is no acceleration. Okay, so this is called Newton's first law, or the law of inertia. We've already talked about the word inertia, but let's revisit that briefly. Inertia is the tendency of an object to continue doing the same thing. These two objects, if this object is at rest, it will continue to be at rest. If this object is in motion, it will continue to be in motion. That is inertia. I previously defined inertia as an object's resistance to change. This resting object does not want to do anything different. This object in motion does not want to be any other way except in that exact type of motion, right? So that is what the word inertia means. It says here, when your car stops suddenly, you keep going until the seatbelt or the windshield stops you. Now, whenever we talk about objects that are in motion, we need to understand that they are moving with some speed and some direction. And so the law of inertia says that they are going to continue moving. So think about whether you are driving or you're the passenger, think about being in the car, and then whoever the driver is suddenly slams on the brakes. You should feel your body moving forward, right? You are going to continue moving forward until there is an unbalanced force that moves you. Now, anytime we use examples that talk about people, people are unique because we have internal muscles and we can control our own motion. So let's say instead, if it's not you, let's think about your backpack. Let's say that your backpack is in the seat next to you. And so the car is moving, the driver slams on the brakes, that backpack continues moving forward because of its inertia. The brakes are applied to the car. The brakes are not applied to the backpack. So the backpack is in motion. It will continue its motion until there is an unbalanced force that changes it. All right, a couple more examples of inertia. If you have ever needed to push a car that is stopped. It says an 18-wheeler stopped at a light. It's harder to get going than a Volkswagen Bug. I like to use the analogy in class if you have a friend who has a vehicle that has broken down, they ran out of gas or something, okay, battery died because they left their lights on or whatever. So if you need to help your friend push the vehicle, if you have a friend that drives a huge truck and you have a friend that drives a smart car or some tiny little, vehicle, a little Volkswagen Bug is what I use in the example on the screen, then the object that has less mass is going to have less inertia. So what we would say as normal people is that, I'm going to offer to help my friend who has the small car because the small car is easier to push. That's right. That is a car that is at rest, and it will continue to stay at rest unless an unbalanced force changes it. You become the source of the force, and you are trying to create an unbalanced force so that you can overcome its inertia. The more massive the object is, the more inertia it has. The second example is no longer talking about cars at rest. Let's say now we are driving. So we have that large truck and we have that small car, and they are both in motion on the road. If they needed to stop suddenly, the force needed to bring the big truck to a stop is going to be much greater than the force that's needed to bring the small car to a stop. So I always tell students, look, whenever you're driving, especially if you're in traffic or if you see traffic coming ahead, do not pull over into the lane next to you if it puts you in front of a big vehicle, especially if you know that you have to slam on your brakes, because you might be able to stop really quickly, but that large vehicle behind you has more inertia because it's more massive, and they may not be able to stop as fast as you, and they might run into the back of you. So we don't want to move in front of big vehicles and then put on our brakes. The place that we can see true inertia would be outer space. So I want you to understand, anytime we talk about being in space, we are going to say that we are in space, but I want you to interpret that as far outer space. And what do I mean by that? We are far enough away from the Earth that Earth's gravitational pull does not affect the object. We're far enough away from the moon that the moon's gravitational pull does not affect the object. That's what I mean when I say in space, okay? So if we have an astronaut that throws an object, this object is going to continue on that path forever and ever and ever because there are no forces acting on it to change its motion. It will exhibit true inertia. Now let's talk about Newton's second law. Newton's second law is called the law of acceleration, and we have this equation F equals ma. Now up here it says that the net force is directly proportional to mass and acceleration. We'll come back and we'll look at what those relationships, directly proportional, inversely proportional, what do they mean and how should we interpret that? But for right now, I want you to look at the equation F equals ma. This is our primary formula for this chapter. We do have a couple of other equations that we will use, but so much of what we're going to do and the calculations we're going to perform are going to come down to our application of this equation. Now it says down here that this force value can be a variety of things. This could be our net force, which we should already understand. If I have a free body diagram and it says I have a horizontal force to the right and a horizontal force to the left, I would then take those two forces and compare them. If they are not the same value, I would need to calculate my net force. So I would say F1 plus F2, where I consider the positive and negative directions, and I would determine whether or not my object accelerated because I have unbalanced forces. So if I have unbalanced forces, that means that I have some net force value, which means that my object is going to accelerate. We learned this on day 1 of this chapter, where we were learning how to draw and interpret free body diagrams. So if we are using this equation where that F represents my net force, I'm going to have to go and figure out what that net force is. I'm going to plug it into the equation, and that's going to allow me to determine what the acceleration rate is for my object. But what if it is not the net force? We've already talked about the different types of forces. So we have FA, FF, FN, FG. Well, what if we make this my FG? This is the force due to gravity. So now when we go to plug in the information for this equation, if this force is going to represent the force due to gravity, that means my acceleration must be my acceleration due to gravity. And so this is actually the situation that we're going to discuss in detail first. Then we'll come back and we'll talk about how to use this equation when that force is the net force. This FC is actually our topic for the next chapter, but I want you to keep in mind that this relationship between force, mass, and acceleration can apply to lots of different situations. It's just a matter of what type of force are we saying is responsible for that acceleration. So let's talk about the force due to gravity. One of the main ideas for this chapter is understanding the difference between mass and weight. So first of all, I want you to know that these are two different variables. Mass is a way of quantifying how much matter it takes to make an object. So if I am holding a pencil, the number of molecules needed to create that pencil would represent the object's mass. So whenever we talk about mass, we're not actually counting atoms, but it's a form of quantifying how much matter is needed to construct that thing. So mass is going to be measured in kilograms, and we're going to use the lowercase letter m to represent mass in our equations. The next variable that we have is weight. Now weight, you can see on the screen, is identified as an FG. That's because weight is a force. Remember, capital F is for force, and then the subscripts tell me the specific types of force. So we have weight, which is the force due to gravity. So our acceleration is going to be gravity. So we are going to say that the weight is the force due to gravity, and so we're going to note that with an F subscript G. Now this is going to be measured in newtons because all forces are measured in newtons. And so it says here on the screen, mass is constant. What that means is that if I have a pen, that pen is comprised of a certain amount of matter. And so if I take that pen to the moon, if I take that pen to Mars, if I take that pen back to Earth, the number of molecules needed to create that pen did not change. So if a pen is constructed of 2.5 kilograms worth of matter, then on the moon it's still 2.5 kilograms worth of matter. And on Mars it's still 2.5 kilograms. That's what we mean when we say mass is constant. The second line here, which has been cut off, says that weight is dependent upon gravity. Now remember, this is technically the acceleration due to gravity. The acceleration due to gravity. So if we are on Earth, the acceleration due to gravity on Earth is negative 9.8 meters per second squared. So when I go to calculate the weight of my object, I am going to consider the Earth's gravitational pull, which causes an acceleration of 9.8. But if I take my pen to the moon, the acceleration due to gravity on the moon is only 1.6 meters per second squared. So that means that the weight of my pen on the moon is different. It's the same mass, but it is experiencing a different gravitational acceleration. So when I consider an object's weight, I must consider where is the object located and what is the acceleration due to gravity at that location. So here it says, because of Newton's second law, we can use F equals ma, where this specifically would be the force due to gravity, and that specifically would be the acceleration due to gravity. So what we are going to say is that the weight of the object is equal to the mass of the object times gravity. We are going to go ahead and just put a G for gravity because there is no other option. My gravitational acceleration is always going to determine the weight of my object. So I am no longer going to say A because A implies that it could be a variety of accelerations. Now, when we are talking about the weight of the object, we are just going to say mg, mass times gravity. It is always going to be times the acceleration due to gravity. So we can see here on the screen we have a couple of practice problems. So let's look at this real quickly. It says calculate the weight of a 3.87 kilogram box on Earth. So we're going to go ahead and follow the guess process here. We have a mass of 3.87 kilograms, and gravity is an acceleration rate, but we're going to go ahead and write it as a G, and that is negative 9.8 meters per second squared. They are asking me to calculate the weight. Remember, we are going to use an FG for the weight, so this is my unknown. F equals ma is our original equation, but because this is specifically the weight of the object, we are going to write our equation as mg. Okay, so we're just going to go straight to Fg equals mg. So I'm calculating the weight of my object by taking the mass and multiplying it by the acceleration rate. So when I do that, I get 3.87 times negative 9.8, and that's going to give me negative 37.926. And so with my sig figs, I would say that the weight of the object is negative 37.9 newtons. Now, you may be thinking, oh, that's weird. Why did she make it a negative? Because remember, when we were learning our free body diagrams, we said that that weight is a downward force. Fg on our free body diagrams is going to point downward. So that should be in the negative direction, and so it should calculate as a negative value. Now, when we look at our substitution, we said that the acceleration due to gravity is downward, and so we used a negative there, and so that calculates a negative force. Now, if we talk about how much we weigh, we don't walk around saying, I weigh negative 200 pounds, I weigh negative 150 pounds. We just talk in terms of the magnitude. So if you read a question in the future, and it says that there is a box with a weight of 37.9 newtons, that's fine. 37.9 newtons is the magnitude. But when you go to do your math work, I want you to remember that these are vector quantities. And so we would put that as a negative 37.9 in our math work. Okay, so then let's look at this next question. Now we are asking you to calculate the weight of the same object. We have the same mass here, but now we want you to take the object to the moon. So on the moon, we have a gravitational acceleration of 1.6 meters per second squared. So now when we go to calculate our weight, remember weight is going to be mass times gravity. So I am going to take my mass and I am going to multiply it by the acceleration rate on the moon. Again, this is a vector value, and so I'm going to make that a negative value of 1.6. So when I take 3.87 and I multiply that by 1.6, I get negative 6.192. Negative 6.192. So that is significantly less than the weight of our object on the moon. Than the weight of the object on the Earth. But if we look at those gravitational accelerations, it is a much weaker acceleration on the moon, so it makes sense that it would weigh less on the moon. Now, this is one interpretation of Newton's second law where we are using F equals ma, and we are specifically using the gravitational force as the F in that equation. But not all second law calculations have to include the weight. What if we are just telling you that we have an object and we have forces acting on an object? What is the acceleration rate because of those forces? So now we're going to go back and we're going to look at Newton's second law again. Here it says acceleration means change in motion. And if you look farther down, you can see, how does our object change its motion? Well, it can change the speed or it can change the direction. So whenever we talk about an object experiencing a change in motion, we're really talking about that object experiencing an acceleration. So Newton's second law is all about understanding what is causing that acceleration and what is the magnitude of that acceleration. So you can see here that a net force is required in order to create an acceleration. So if we think back to our free body diagrams, if we had some net force value where these forces were unbalanced, we were able to calculate a net force value, and this meant that my object experienced an acceleration. If we have a situation where these two forces are balanced, now our net force value is 0, which means that there is no overall effect because these two forces canceled each other out. So our object will experience no change in motion, or there will be no acceleration. So this is the same concept that we are applying to Newton's second law. Now what we are saying is the acceleration rate that the object experiences is dependent upon the net force. So I must consider both forces to determine how much it accelerates. It says here acceleration is directly proportional to force and inversely proportional to mass. So here's a quick, easy way to understand what those relationships should be. If I take my equation, F net is equal to mass times acceleration, and I do some algebra in order to solve for my acceleration, I would basically divide both sides by mass. So my acceleration is going to be force divided by mass. So when it says the acceleration is directly proportional, here's what that means. If I increase my acceleration, it means I must also increase my force. They both increase together. If I decrease the force applied to my object, then the object will experience a lesser acceleration. So they will both decrease together. So this is what we mean when we say directly proportional. For my math brain people, if we look at this equation, I'm going to rewrite this where A is part of a fraction. So this is the A for acceleration in the numerator and then the number 1 in the denominator. I can see that force and acceleration are both currently listed in the numerator of their fractions. Now this method only works if you have your two variables on opposite sides of the equation. We have to have them set equal to each other. So because they are both in the numerator, that would make them directly proportional. And so it means if I increase one, the other increases. So then let's look at the other half of this sentence. Acceleration is inversely proportional to the object's mass. So now, if we were to consider our acceleration and our mass, now what this is saying is if I increase the acceleration rate, it must be because it was a lesser mass, or what we will actually see more often is if I have a less massive object. As a result of that, my object will experience a greater acceleration. Now, this is assuming that the force is the same on both. So let's say that you have me, Ms. Espinosa, and you have Mr. Mullen, our principal, and we are both standing in the hallway, and a student bumps into the two of us. We both experience the same force from that student bumping into us. But Mr. Mullen has a different mass than I do. So his acceleration is going to be different than my acceleration because his mass is going to receive that force and he will have a very small, minimal, maybe no acceleration at all. If I experience the same force, then it is likely that I am going to experience a more noticeable acceleration. My acceleration would be greater because less massive objects experience a greater acceleration. More massive objects experience a lesser acceleration. So this is what it means to be inversely proportional. Inverse means opposites. So if we have this equation here where it's set up for A equals F over M, now my acceleration and my mass are not both in the numerator. Again, this only works if I have them set equal to each other, but my acceleration is in the numerator and my mass is in the denominator. They are in opposite parts of the fraction, so that means they are going to experience opposite changes in their values. So inversely proportional means opposite. One increases, the other decreases. Directly proportional means that they are going to experience the same types of changes in those values. We have some illustrations here. We'll come back to this one. Actually, let's do this one first. If I have a car and I'm driving in my car, here it says that the mass is the same for both of these. So if my car has the same mass, equal masses, but I experience a different force, then that is going to change the acceleration rate. So if you are driving your car one day at school or on the way to school and you are sitting at a red light and you very carefully press on the gas pedal, you produce a small force acting on your car's mass, then your car is going to have a small acceleration. We're going to come out of that red light, that stopped position, nice and slowly. It's a small change in our velocity. But if I were to be in the same car, so the mass is the same, but now I press really hard and fast on that gas pedal, well, I'm applying a greater force to my car. So if I apply a large force to this mass, as a result of that, my car is going to experience a large acceleration. We are now going to have a very sudden change in our speed over time. Okay, so that's what that means for them to be directly proportional. If we look at this elephant, and we're going to call this a rock, here it says my two objects have equal accelerations. So if the accelerations on our objects are the same, now if we consider the fact that these accelerations are the same, let's say that these objects are in free fall, where we know that this value is negative 9.8 for both situations, right? Then that means that the more massive elephant is going to experience the same acceleration rate as the rock over here if a very large force is applied to my very massive elephant, and at the same time a very small force is applied to my very small massed rock. We can also think about this in terms of the vocabulary weight. If we talk about the weight of my elephant, it makes sense to say because the elephant is more massive and this acceleration rate is really gravity, the more massive elephant has a greater weight, because when I go to calculate the weight of the rock, the less massive rock experiencing the same negative 9.8 meters per second squared for its acceleration, is going to have a smaller force acting on it. So I want you to understand that Newton's second law can tell me about forces acting on an object, and then we can calculate the acceleration rate, and it can also be used to help us understand the weight of the object, because if the object is falling, then the force needed to pull that object so that it accelerates at the rate of gravity would be larger for more massive objects and smaller for less massive. All right, Newton's third law, the law of action-reaction. It says here for every action force, there is an equal and opposite reaction force. So basically, if I have my phone sitting on the table, my phone presses down on the table, and as a result of that, the table is going to press up on the phone. Newton's third law must include two different objects, and the forces are going to be applied onto each of the object from the other. So here it says if object A applies a force onto object B, object B, so see now I've switched objects, object B is now going to apply a force back onto object A. These are going to be equal magnitudes but opposite directions. That's what Newton's third law says. So if we look at this example of a hammer hitting a nail, the action force is that the hammer hits the nail. A lot of students would want to tell me that the reaction is that the nail goes into the wood. Every third law action-reaction pair must have two different objects, each of them experiencing a force. So my two objects in this example are the hammer and the nail. So if the action statement is that the hammer applies a force onto the nail, then the reaction statement is that the nail applies a force onto the hammer. So if we look at this picture, the soccer ball is kicked into the net. So the action force is that the ball applies a force onto the net, and so the reaction is that the net applies a force onto the ball. They are equal in magnitude but opposite in direction. We are really just writing an opposite sentence. Here we have the guys running. The foot applies a force down onto the ground. So, as a result of that, Newton's third law says the ground applies a force upward onto the guy's foot. So there is your action-reaction pair. Again, two objects, the foot and the ground. They each experience a force. Okay, so those are Newton's three laws, and we could talk about these different pictures, and we should be able to identify what are all of Newton's laws. Where is an object at rest unless a force changes it? Where is the object in motion unless the unbalanced force changes it? Where is there a force causing an object to accelerate? Where is there an object experience a force due to gravity because it has a weight? Where do we have equal and opposite force pairs? So at this time, you have learned all three of Newton's laws. Number one is the law of inertia. Number two is the law of acceleration. Number three is the law of action-reaction. And we should be able to interpret these situations in these laws in various situations. All right, so we're now going to cover the last little bit of Newton's laws and force information. Just to kind of review, because of Newton's third law, we know that the frictional force is always opposite the motion of the object. Because of the contact between those two surfaces, they are rubbing against one another in opposite directions. So that is our frictional force. In this class, we are going to have our objects sitting on top of flat horizontal surfaces. So a book on top of the table, a ball rolling on the ground, a car on the road. So because we are going to have our surfaces nice and flat and horizontal, for us, our normal force, that force from the table up on the object, is going to be in the opposite direction of gravity. We're keeping it very simple for y'all. Now, here we have a variety of forces acting on our object, and it says if the object has a mass of 5 kilograms, what acceleration will it experience? So on the vertical axis, these two force vectors are the same. If I were to calculate my net force, remember that's F1 plus F2. So in this case, my net force would be a positive 25 because my normal force is upward. And it would be a negative 25 because gravity pulls down on our objects. So if I add these two together, that is going to give me a value of 0 newtons, which means my forces are balanced. There is no acceleration. So there's no acceleration in the vertical axis. But what about the horizontal axis? This has a value of 40 newtons, and over here we have a value of just 10 newtons. So this was an existing picture that I grabbed and threw some numbers on it. So this force vector would actually be smaller over here than it is on the applied side. So now whenever we get ready to calculate what is the acceleration on the vertical axis, the horizontal axis, now once again we are going to calculate our net force. I'll do that over here actually. We're going to calculate our net force by saying F1 plus F2, where F1 is a negative 10 because this is our frictional force, and F2 is a positive 40 because that is the applied force. This gives me a value of a positive 30 newtons. So my net force, the force that is actually going to cause my object to experience its acceleration, it's going to be 30 newtons of force that makes that happen, okay? So whenever I get ready to calculate what that acceleration rate is, I'm going to use F equals ma, but now my net force is going to be the 30 newtons from the previous calculation. So 30 newtons equals 5 times A. So then I would divide both sides by 5, and that's going to give me my acceleration is equal to 6 meters per second squared on the horizontal axis specifically. Okay, so now we're going to talk about friction. This is the last bit of information for this chapter. So you see here we have something called the coefficient of friction. Friction occurs because there is contact between two materials, and there's typically some sort of rubbing force that takes place because they are in opposite directions. So if we are talking about trying to move the desk in the classroom, we know that there is friction between the desk and the floor. That desk has some amount of initial friction because it is sitting in contact with the floor. There is some sort of friction that is there. And if that object is at rest, we are going to refer to it as static friction. If you've ever tried to move a desk or a heavy table, you understand that initially there's some amount of friction that is making it awfully difficult for you to put it into motion. So static friction is for objects that are already at rest. Once you get that object moving, if you've ever had to move a very, very heavy thing, by either pushing or pulling it, I want you to think about that moment right now. If you've ever had to pull or push something that is very heavy, once you get that object into motion, you don't want to stop because there is a different amount of frictional force that is experienced whenever our objects are moving. So frictional forces, because the object is in motion, we are going to refer to that as kinetic. Kinetic means moving, okay? So kinetic friction is going to be anytime we have frictional force for a moving object. We have a new equation here. Our equation says the frictional force, F of F, and this really should be F with the subscript F. Sorry, the font doesn't like the subscripts when I transfer the file. So F of F is the frictional force, and that is equal to, now this coefficient of friction is a new variable for us, and it is pronounced mu. This does not have a unit. There is no unit for the coefficient of friction, and we'll talk about why that is with one of our examples in a moment. Mu times the mass due to gravity. Again, we want that mass to be in kilograms. And then we have g, which is the acceleration due to gravity. So this is going to depend on where the object is located. Are we on the moon? Are we on Earth? Are we somewhere else? Somewhere in the problem, that information needs to be provided for you.